Hello everyone! In a previous video, we learned about linear interpolation and how we can use it to move our player character from the start position to a target position. So very quickly, what this demo does is it has two vectors, the target and the start. Every time I press the reset button, the start is set to the player position, target is randomized, and the heart's position is set to the target so that we can see what the target is. Yeah. And then every frame we're using linear interpolation to move from the start to the target. And so this is nice and all, but this requires us to remember what the start position is and how much time has passed and how much time we want it to be. Sometimes we just want to get quickly to a target position without actually knowing exactly how long, but we don't want it to be like going at a constant speed because that can be quite slow. So in those cases, what can we do? And here is my secret technique, which is exponential decay. And this sounds very scary, but it's actually pretty simple. I mean, you can just copy the formula once we get to it. But understanding the formula is the fun part, and we do use some exponentials. So the idea is that imagine that we start at 1 and we want to reach 0. One way to do it is that every frame we multiply by like 0.99. Because if we keep doing so, this will get smaller and smaller. But the thing is that no matter how big my number is, or how small it is at the beginning, we're always going to go back to 0 if we keep multiplying by a number that is less than 1. And this is going to be faster the farther away we are, and slower the closer we get. So even if we start very far away, this is going to be a fairly quick process. The issue with this is that we are using a constant for every frame. But the frames might be faster or slower depending on the frame rate. So we want to do this in a way that is independent of the frame rate. And this is when we learn about exponential decay. So exponential decay is something that happens in physics and in mathematics. For example, with radiation. So if you have something that is radioactive, its radioactivity will decrease over time, but this is not linear, it's an exponential decay, which will look like the exponential function. So what does it does reach, well, it never reaches 0, but it gets very, very close to 0 the further away you go. And so the exp function looks like this. It starts very close to 0, and then it grows very, very quickly. Exponential decay is basically exp of minus x times some constant, which is usually called lambda, but I've been using lambda for something different, so let's just call it speed. So that would be s is equal to speed. And so essentially, this minus here, what it does is it flips this horizontally so that we get this kind of curve. Which again, it kind of goes from here, but we're only interested in the positive part. And so the question then is, what is this parameter here that we need to use? And this parameter is going to be based on this, well, this delta, which is the time that has passed since the previous frame, is precisely how much we need to move. That's how much we need to multiply it by. And so the multiplier is the exponential of minus the speed times delta, which is how much time has passed since the previous frame, multiplied by how fast we want to go overall. Still using this minus. Okay. But this is if we want to go from like 1 to 0 what happens if we want to go from A to B? And this is where linear interpolation comes in helpful. So once again, if we want to go from A to B, linear interpolation is going to give us that this at lambda is equal to, I don't know. So this would be lambda equals to a half. This would be lambda equals to a quarter. This is at lambda is equal to 0, and so on and so forth. And so we have this multiplier. That is when we want to go from 1 to 0. So if we want to go from A to B, this is going to be like lambda is going to be equal to 1 minus the exponential minus the speed times delta. So essentially every frame we're getting a little bit closer. And so instead of multiplying by 0.9, we're multiplying by 0.01, for example. But another way to do this is to use linear interpolation the other way. And so kind of like going from B to A and multiplying by this exp of minus speed times delta, which is again a number very close to 1, it's like 0.99. And since it is now going from B to A, it's going to be something very close to A. So how does that work in practice? Well, first we can remove all of the time parameters. We can also remove the start. We're no longer going to need it. We no longer need to advance time, but we will need our delta. And now the player position is going to be a linear interpolation. Usually it goes from the start to the target, but once again, we're now going from the end to the beginning. So from the target to the start, but this is no longer the start. This is now the player's position. Because every time we're getting closer by this factor, by using the player's position instead of the start. So that's why we no longer need the start, and why this is a technique that is quite useful. Because we need like fewer things. We don't need the start, we only need the target. And now what is this lambda? It's going to be the exponential of minus delta times the speed. And this speed, let's set it to like 10 for now. So let's see how it goes. It should go very quickly towards the objective, but then slow down as we reach the objective. Yep. So this is really quick, and it slows down as we get close to the objective, which is really nice. So for example, let's see what happens at different speeds. So now the speed is 2. It's much slower, but it still goes fast and then slows down as we get close to it. So by adjusting this speed, we can get different results. But what is important about this is that no matter how far we are, we always get there relatively quickly. If it's far away, it doesn't take like 5 seconds getting there. And that's because of this exponential decay. It gets really close to 0 no matter where you started. Okay. And this is the formula that you will learn to love. And it is very, very useful for many different things. Especially since we don't have a start, we only have a target. If you have something that follows something else, like for example the camera that follows the player, this makes it so that it is following after the player, a little bit behind, never staying too far away from the player, because it is very quick if it is far away from it, but it is quite smooth. So it is a very nice way to control cameras, for example. And yeah, I hope you enjoyed this secret formula.